When we wish to adapt these, we need to understand the pieces that come into play that set those initial permissions. The first of these is whether you're creating a regular file or a directory. The second thing that impacts these permissions is something called the current UMask. If you create a new directory, an operating system will start by assigning its octal permissions 0777 or full access to that directory. If you create a new regular file, the operating system designates the original octal permissions 0666 or full read and write permissions, but no execution. When it comes to files, you'll always need to explicitly set the execution bit so we don't end up with rogue scripts or malware infecting our environment. Once the file has initialized with these default permissions, the UMask then comes into play. This is what we call a bit mask, and we'll use to overlay the permissions to adapt them to the proper initial permissions we wish to set in our environments. Consider the following output from the UMask command. Here, the execution of UMask shows 0002. This is an octal representation of the value of the current bit mask that will be applied. You can omit any leading zeros in the UMask before understanding what will be set. Default values for all UMasks in the bash shell are set in a few files, etc profile and etc bash rc. You can override these default values with your own local users' hidden files .bash profile and .bash rc. Let's look at an example of what the UMask does when creating new files and directories. Given this output, we can see the UMask is currently set to 0002 or 2. When we create a new file named default, we can view its initial permissions as read write, and read. When we create a new directory named default, we can view its permissions as read write and execute for both user and group, and read and execute for other. When we adapt the UMask value from 0002 to simply 0, and then create files and directories, we should be able to understand the difference in the permissions that get created. Here, we'll touch a 0.txt file. We can then see that the resulting permissions allow us to have a write permission for other. This was not in place originally. Additionally, when we create a directory, we see that the permission includes full permissions for all user, group, and other. Initially, with a UMask of 2, we removed the write permission for other. Now, with the UMask set to 0, we allow the creation of all permissions when we create a directory. If we were to want to mask all the file and directory permissions for the other permissions, we could set the UMask value to 7. The value of the UMask is the removal of those bits no matter what is created on the initial file. When we set a UMask value to 007, we're denoting that the other bits should all be removed, read, write, and execute, and that no permission should be extended to others. Here we can see an example of that being used. The UMask is set to 007, and then, when a file is touched, we strip away all permissions for other. The same is true for directories. With a UMask of 7, all permissions are stripped away from the other access. A UMask of 027 would result in all permissions being stripped from other and the write permission being stripped from group. In the output below, after the UMask is set, you can see that the group permissions do not include write and the other permissions have none. As the root user, you can update the etc profile.d local umask.sh. This will allow an adaptation of the default values that get supplied when you create new files and directories. It is in this fashion that you can adapt your operating system to properly put permissions in place when creating new files and folders that conform to the standards of access you wish in your environment. That concludes this section. Join me in the next video where we explore these new skills in a guided exercise.